Hi, so the next video I wanted to do is try to solve one of the practice questions from the practice questions for the exam on the MVCLT. So the practice question that I'll be doing is 1C. And the key part of this that makes me think, okay, we want to apply the multivariate CLT is it asks, I'll write this down in case you don't have it in front of you, asymptotic distribution of the square root of n times y n minus mu as n goes to infinity, right? If you see something that looks like this, there's a very good chance that we're looking to apply the multivariate CLT. It also gives in the problem that this mu guy is equal to the vector that is CDF at A1, CDF at A2 to the CDF at AN. AK, sorry, and Y is the observed CDF through n samples at A1 and the observed CDF through n samples at A2 up to, again, AK. Right, so what are the criteria for, or what are the components of the multivariate CLT? Well, let me write that down. We have that square root of n times x minus mu converges in distribution to multivariate normal with the zero vector as the mean vector and the original covariance matrix is the covariance matrix. So we have the square root of n, check. Now to decide whether this is what we want and this is what we want, I think it's worth talking more about what exactly the problem is asking. And this is by no means supposed to be a comprehensive explanation of what the entirety of problem 1, but y sub n, as I said earlier, is the observed number of samples through n that are less than or equal to A1, while next entry in this matrix, I'm just writing what the Fn hat is by definition. So same thing, but less than A2, same thing, less than A3, while mu hat is what the true proportion, or what the true CDF at A1 is, and what A2 is. So true CDF at A1, true CDF at A2, and so on. So if you imagine that yn is the I guess I should clarify. I was a bit lazy with the notation for yn. It's not the observed number of samples, it's the observed proportion of samples. So if you view each entry in yn as a random variable, right, because there is some probability when you sample from this distribution that it will be greater than A1 or A2 or any of these AKs, and some probability that it will be less than each of these, right? And it's random because we're sampling from it. That means that each entry in the yn vector is going to be a random variable. And the expected value of that, as what makes intuitive sense, is the proportion of, or the true CDF at that point, right? Because probability that a random sample from this, I'll call it xi, that's less than A1, is by definition less than or equal to A1, is by definition the CDF at A1, right, which is what we have in here, and the what we've observed so far. So the observed CDF at this point is the fx hat at A1, which is what we have in here. Again, the takeaway from this isn't necessarily me explaining the entire thought process for this problem, but just providing some justification for why we're using the CLT here. So then, by that MVCLT, we have square root of n of yn minus mu converges in distribution, which is the same as saying as n goes to infinity, what is the asymptotic distribution of this, to multivariate normal with mean. I shouldn't write that. I should just write the zero vector. It's the mean vector. And the original covariance matrix is the covariance matrix. Now, to express what is the covariance matrix, you would have to note that actually what I think I'm going to do is make a video on question 1A to talk more about that. So save that for a future video.